Okay, now we have the last question, question 4 on the 2026 AP Physics 2 free response section. Here we have equal potential lines for a region with an electric field, and we have a small sphere with positive charge Q. Initially at point S with the speed v sub s in the positive x direction and a kinetic energy k sub s. And the sphere will end up at point T. And the electric field is the only force exerted on the sphere as it moves between S and T. So when the sphere reaches point T, it'll have a final speed v sub t and a kinetic energy k sub t. So for part A, we need to indicate whether Vt is greater than, less than, or equal to. Okay, so it seems like if we have the positive charge here, moving with speed Vs, it looks like it's going from a region of low potential to high potential. And so there's probably some sort of negatively charged region out here and some sort of positively charged region out here. So I would imagine it's actually going to be a lot slower at point T. So someone must have given it an initial velocity at point S, and then that should decrease in magnitude as it moves from S to T. So here I would imagine it's going to be going a lot slower compared to S. So Vt should be less than Vs. And so let's actually start that for part A on another page. So we'll say for part A, Vt should be much less than Vs. And the reason is positive charges increase in electric potential energy. As they move from low potential to high potential. And so because of that, the electric potential energy is going to increase, and therefore the kinetic energy should decrease. So we can say due to conservation of energy, the kinetic energy should decrease as the electric potential energy increases. And so if the kinetic energy does in fact decrease, then the speed should be slower. So we'll say with a lower kinetic energy, the speed will be slower. That should do it. Energy at point T, the speed should be slower. And that should do it for part A. All right, part B. Drive an expression for the kinetic energy at point T in terms of V naught, Q, and Ks, and physical constants as appropriate. Perfect. Okay, so we will actually do this quantitatively. So we're going to start at an energy of -3 V naught and end at a potential energy of 2 V naught. Okay, so for part B, just to get a bird's eye view of what's going on, the initial electric potential energy should be positive Q times an energy of, or potential of -3 V naught. And the final electric potential energy should be positive Q times a potential of 2 V naught. And then the initial kinetic energy is Ks. And then the final kinetic energy should be the expression we're actually trying to solve here. So we can say conservation of energy as our fundamental concept. And so we'll say the initial electric potential energy plus the initial kinetic energy should equal the final electric potential energy plus the final kinetic energy. So our initial is negative 3 QV naught plus the initial kinetic energy should equal 2 QV naught plus our final kinetic energy at point T. So therefore, our final kinetic energy at point T is equal to Ks minus 5 Q V naught. And that should do it for the derivation in terms of Ks, Q, and V naughts. Perfect. Okay. Then on to part C. So we have a new small sphere of the same mass as the original sphere, but with a negative charge with the same initial speed Vs. Okay, so we're going to repeat the experiment, but have a negative charge at point S. The electric field is the only force exerted on the new sphere between points T and S. And the new sphere is going to have a new kinetic energy when it's at point T. Well, negative charges, when they move from regions of low potential to high potential, actually get faster, because that should technically be a decrease in electric potential energy. And we can kind of see the negative charge should accelerate as it moves from a region of negative charge creating the negative potentials to a region of positive charge creating the positive potentials. And let's see if that actually matches with our derivation in part B. Yeah, we have to justify using our derivation in part B. Okay. So in part B, we said our expression was A sub T is equal to the initial kinetic energy minus 5 QV naughts. But in this particular case, our charge is actually going to become negatively charged. So that should be Ks minus 5 times negative Q V naught. And I believe when you multiply those two negative signs together, you're actually going to get the initial kinetic energy plus this change in electric potential energy. And so it seems like by changing the charge of the sign of the charge, so by changing the sign of the charge, negative charge will actually lose electric potential energy moving from S to T. And therefore gain kinetic energy. By substituting negative Q into our expression of part B, we see that the new kinetic energy is indeed larger. Into the derived expression from part B. You see, oops, Ku is larger. Awesome. We should actually clean this up a little bit and say this is from part B. This is our answer to C, and we should say our claim is, in fact, that K nu is larger than K sub T. And I think that should do it for question 4.